announcements, please send the message. So to subscribe, send email or a WhatsApp message with subject or text webinar to geodiff@unicamp.br -myself. Okay, so there's various ways to subscribe, and we're adding a new feature. So we're going to be sending Google invites to everyone who subscribes to the WhatsApp group, so you can add them automatically to your calendar. It's effortless. But for that you need to subscribe to the WhatsApp group. Bear in mind these options are strictly closed. They're strictly admin managed, so there won't be any spam, any other information broadcast besides what's immediately relevant to the South American webinar. Okay, so all the details are here on the chat. So without further ado, let me introduce our good friend Gonçalo Oliveira from UFI, Fluminense Federal University. He's going to be telling us about special Lagrangians, Lagrangian mean curvature flow, and stability conditions.
Well, thank you, Enrique. So first of all, let me just, so I was going to speak about Lagrangians, special Lagrangians, Lagrangian mean curvature flow, and relations with Bridgeland stability conditions on Fukaya categories. Some work in progress that Jason Lotay and myself are doing. But given that I found it difficult to speak about this later work we have been doing without speaking about our earlier work, which appeared first on Archive earlier this year, I decided to maybe stick to our earlier work, which may be more, and it may be more appropriate for me to do that. So I'm going to start sharing my screen with you so that I can show you the slides. Okay, so is this working? Can someone tell me whether this is working or not?
This is great.
Yes, working.
Okay, cool. So I'm going to put it to full screen. Okay, so this is the title. First, let me hide this. Okay, so in this first slide is going to be kind of like a mini talk. It's a prelude, as it says there. It's a mini talk, and then I'll go later to say all the things I'm going to say in this slide in more detail. But here I want to tell you already what are the main results and what this work consists on. So Calabi-Yau manifolds are a special class of Riemannian and symplectic manifolds. They are both Riemannian and symplectic in a very special way. And there is a family of submanifolds of them called Lagrangian submanifolds. They should be thought, if you think of symplectic manifolds as generalized phase spaces of mechanical systems, then maybe Lagrangian submanifolds, you should think of them as generalized configuration spaces. And inside the class of Lagrangian submanifolds, in a Calabi-Yau manifold, there is a special class of them called the special Lagrangians, okay? So I said distinguished here to not say the word special twice, but that's a special class of Lagrangian submanifolds that are called special Lagrangians. And these have been important both in mathematics and in physics, in mostly theoretical physics. And for instance, mathematically, these special Lagrangians, besides being Lagrangians, they are volume minimizing. And so they are important not only from symplectic aspects, but also in Riemannian ones. So they are interesting Riemannian objects as well. So In particular, they are minimal submanifolds. And the central question, if you are a symplectic geometer, you would like to think of Lagrangian submanifold up to equivalence. So you would like to think of Lagrangian submanifolds that are Hamiltonian isotopic as being more or less the same. So that's, maybe Renato can tell you more about that. But so you will be interested not in a Lagrangian submanifold, but in an Hamiltonian isotopic class of Lagrangians. And then a question you can ask is whether there is a best representative of an Hamiltonian isotopic class of Lagrangians. And given that special Lagrangians minimize volume, you may think that maybe they are the candidates to be the special representative of an Hamiltonian isotopic class. But then it arises the question of whether you can even represent a given Lagrangian Hamiltonian isotopic class by special Lagrangians, by one, maybe more special Lagrangians. And so this is the central question I'll be focusing on in this talk, in some examples. And one way to try to answer this question is to look back at the reason why special Lagrangians are interesting by physical reasons. What is it that physics has to say about them? And in physics, there is this thing called mirror symmetry, under which the Lagrangians are mirror symmetric to compatible connections on holomorphic vector bundles. I put it in inverted commas here because it should really be holomorphic sheaves, but for the sake of simplicity, let's think of them as being mirror symmetric to compatible connections on holomorphic vector bundles. Compatible here meaning with the holomorphic structure. And then the special Lagrangians, they correspond to the Hermitian and Mills connections, which is a particular kind of compatible connections. So it's not so important that you understand these things I'm talking about right now, but let me show you some special effects that I made. What is it? So here are the special effects. So this is a diagram of mirror symmetry. So you have here an Hamiltonian isotopic class of Lagrangians, and then the special Lagrangians inside them, and then you map them to the mirror, and on the other side you have these connections on an holomorphic vector bundle, and the special Lagrangians get mapped to the so-called Hermitian and Mills connection. These are connections that satisfy the Hermitian and Mills equation. And so in order to understand whether an Hamiltonian isotopic class can be represented by a special Lagrangian, maybe you would like to look here and see when does an holomorphic vector bundle admit a compatible connection that satisfies the Hermitian and Mills equations. And in this side of the mirror, this is understood. This side here is understood, and what comes here is something called the Ishin-Kobayashi correspondence. So there is a theorem of Donaldson, Uhlenbeck, and Yau that tells you that if you have an holomorphic vector bundle that is stable, then you can find a compatible connection that satisfies the Hermitian and Mills connections. So based on this, yes, please.
So question from me. Can you perhaps give an idea of how the mirror works? Maybe not everyone knows how a submanifold can correspond to a connection on a vector bundle.
Yeah, I also don't know very well how it works. But that comes from homological mirror symmetry, which at the time Thomas posed this conjecture was already around, that there are these categories that are equivalent. But if I go on and talk about that, I don't think it's going to help very much. I just want to, the goal of this slide is maybe to just tell you that there is this thing called stability that in the mirror side controls the existence of an Hermitian and Mills connection. And based on that, Richard Thomas conjectured that there is maybe some notion of stability on this other side that controls the existence of a special Lagrangian in an Hamiltonian isotopic class.
Okay, so let's settle this. So Marcus Jardim is offering to clarify this a bit. So during the questions, I'm going to have him ask and answer the first question, and then we can move on from here.
Okay.
Thank you, Marcus.
Okay, so let me go back to this.
Yeah.
Okay, but it's mostly irrelevant for what I'm going to tell about the mirror site. I'm gonna forget about the mirror site from now on, just to tell you where this intuition, where this conjecture comes from. So the conjecture stated here says that there exists in an Hamiltonian isotopic class of Lagrangians, you can find a special Lagrangian if and only if that Hamiltonian isotopic class of Lagrangians was stable. So that is the Thomas conjecture, and I will tell you later on in the talk what stability really means here, okay? Then elaborating on this conjecture, there was later another conjecture, now of Richard Thomas and Yao, which goes more or less in the following way. So let's say you start with a Lagrangian in an Hamiltonian isotopic class, and you want to somehow deform it and until you find the possible special Lagrangian representative of it, okay? So what you would like to do, given that the special Lagrangian minimized volume, is follow some flow that minimizes the volume, and the one that does that the fastest is the one that is the negative gradient flow of the volume functional. And using that flow, you would like to find the special Lagrangian representative of that class if it exists. So that flow is called the Lagrangian mean curvature flow. And the Thomas-Yao conjecture says that the Lagrangian mean curvature flow, starting at the flow stable Lagrangian, so flow stable because the notion of stability for the flow is slightly different, exists for all time and converges to the unique special Lagrangian from the original Thomas conjecture. Yes?
So we have a question from Luis Diogo. So in Hitchin Kobayashi, do you get the unique Hermitian and Mills connection?
Mm-hmm. Yes.
Great.
Yes.
He says cheers.
Thank you. Okay, so and Jason and myself will give proofs of both of these conjectures in some cases. Okay, under some condition, under some assumptions. So versions of these conjectures have become theorems. Okay, so one thing that I must say is that the Thomas-Yao conjecture cannot be true. Andre Neves showed that it cannot be true, and it must be corrected, but also follows from the work of Andre Neves one extra condition that you need to add to the Thomas-Yao conjecture. So one extra hypothesis you need to add, at least that thing you need to add, and under that extra thing we can prove it in these special cases. Okay, so let's go on to the main part of the talk, which is to tell you what these things are more precisely. Okay, so let's start with what is the Calabi-Yau manifolds we are interested. So a Riemannian form manifold with finite fundamental group is called Calabi-Yau if it comes equipped with 3 compatible symplectic structures, omega 1, omega 2, omega 3, such that the associated almost complex structures, I1, I2, and I3, satisfy the quaternionic relations. So they are associated via this equation, right? And they must satisfy the quaternionic relations, which is I1 times I2 is I3, and cyclic permutations of this. Okay, so you may be, if you are familiar with what an hyperkähler form manifold is, this is exactly the same thing, and the reason is because Calabi-Yaus in real dimension 4 and hyperkählers in real dimension 4 are the same thing, because SU2 is the same thing as SP1, and also these almost complex structures turn out to be integrable. That comes from the quaternionic relations and these structures being symplectic. So the fact that they are closed and they are tied up together with the quaternionic relations actually force these almost complex structures to be integrable. And then let's say you fix one of them. There is no loss of generality in picking one rather than 2 or 3. Then G, I1, and omega 1 is a Kähler manifold. and G is a Ricci-Flat metric. So it's a Ricci-Flat scalar metric, and the holomorphic volume form, whose real part is omega-2 and whose imaginary part is omega-3, has constant norm, and it's holomorphic. So this makes the link, maybe if you are more familiar with other definitions of Calabi-Yau manifolds, maybe this lower part makes it more familiar for you. Okay, and the Calabi-Yau for manifolds we will be considering are all of those which admit a circle action that preserves all these symplectic structures and the metric. Okay, so all the structure must be preserved by this circle action. So we are going to consider all such four manifolds, and there are infinite families of them. There are many examples. If you are familiar with some names, I wrote here some examples. For example, the multi-Eguchi-Hansen manifolds and the multi-Taub-Nutt. But there are infinite families of examples. And as I go on and tell you how we prove the results that I'm going to state, I'll give you a bit more hint on how these manifolds look like. But R4, for example, is an obvious example, but here are some more interesting ones. Okay, so given the existence of these infinite families of examples, this is a good testing ground for the Thomas and the Thomas-Yau conjectures, which is what we are going to investigate. So from now on, our manifold is going to be one of these. And let's now go on and see what Lagrangians, special Lagrangians, and stability really mean. Okay, so an oriented embedded surface in a symplectic manifold X for omega-1, seen as a symplectic manifold, as before, is Lagrangian if the restriction of the symplectic form omega-1 to it vanishes. Okay. The Lagrangian angle is the circle-valued function such that this equation here holds. So if you pick this thing here, which is the holomorphic volume form, and you restrict it to the Lagrangian, that thing has norm 1, okay? So if it has norm 1, and if it's a complex valued form, then it must differ from the Riemannian volume element by a unit complex number. And the family of those unit complex numbers forms a circle-valued function, which is called the Lagrangian angle. Okay, so that's what the Lagrangian angle is. And now I'm going to say that a manifold, another Lagrangian submanifold, is Hamiltonian isotopic to L, and I'll write that with a tilde, if there exists an isotopy, a family of an isotopy of X, which is symplectic, so preserves the symplectic form, and brings L to L prime. Okay, so are there any questions so far on these two things? If there are questions, please feel free to interrupt me. Okay, so.
Okay, can go on.
Okay, so, and then what is a special Lagrangian? A special Lagrangian is an oriented Lagrangian which has constant Lagrangian angles. So the Lagrangian angle is not really, it's a constant function. Okay. So, and you may notice.
Where the symplectic morphism to be Hamiltonian on your definition?
Sorry?
Don't you require the isotopy to be Hamiltonian?
Oh, I have pi 1 finite here, you see? So that is true.
Okay.
Pi 1 is finite, so that it is yeah. It is Hamiltonian. Yes. I just wrote it this way so it's easier to state, okay? So that I don't need to explain what Hamiltonian really is in general, okay? But thank you. So a special Lagrangian is an oriented Lagrangian consider a Lagrangian angle. And if you look at this equation here, then you may pass e to the I beta to the other side, and then this thing becomes a real volume form until you can rewrite that equation in this way, okay? And it turns out this thing in the left-hand side is a calibration. So this thing here tells you already that special Lagrangians minimize volume in their homology class. if you are interested in seeing a proof of this, let me know, and I have some special effects to show this. If not, I'll go on and continue without showing you a proof of this.
Go ahead.
Yeah.
I think you can go ahead.
Sorry?
I think you can go ahead.
I can go ahead and not show a proof of this. Okay. But in any case, if someone wants to see a proof of this either now or at the end of the talk, let me know, and I have a slide with that. So, and on the other hand, if you know that a Lagrangian is Hamiltonian isotopic to a special Lagrangian, then that means that the Lagrangian angle, it's homotopic to a constant function. So you can actually lift the circle valued function to a real valued function, and such a lift is something called a grading. Okay? So that's what a grading is, and all Lagrangians will be graded from now on. Okay? And one construction important to understand the notion of stability, at least as defined by Richard Thomas, is the notion of connect summing Lagrangian submanifolds. So there is something called the connect sum of Lagrangian submanifolds. So topologically, this is just a connect sum, but symplectically, it involves choices, and there are two different ways to do it. L1 connects in this dimension. L1 connect sum L2 need not be Hamiltonian isotopic to L2 connect sum L1. Okay, so this is important. But I'll show you in examples what this means. Okay, and a Lagrangian is called unstable if it is Hamiltonian isotopic to a Lagrangian connect sum, such that the average grading in this way of the first one is greater or equal than that of the second. Okay, so we say that the Lagrangian is unstable if I can break it as a Lagrangian connect sum in its Hamiltonian isotopic class, with the average grading of the first being greater than that of the second. Okay, so that's what unstable means, and it is stable if there is no way to break it such that this happens. Okay, so you may be able to break it a stable Lagrangian. You may be able to break it as a Lagrangian connect sum, but if you can do that, then the average grading of the first needs to be smaller than that of the second. Okay, just to clarify the definition. So is this clear? Are there questions in this slide before I continue?
Okay, good.
Okay, so let's continue. And so results. So just recall that all our Calabi-Yaus have a circle symmetry, and our results are also only concern the circle invariant setting. So the first result from Jason and myself is that if you start with a circle invariant Lagrangian sphere in one of these manifolds, then considering only circle invariant Lagrangians and circle invariant Hamiltonian isotopies, it is Hamiltonian isotopic to a special Lagrangian if and only if it is stable. And in this situation, the special Lagrangian is unique. So this proves a version of the first Thomas conjecture. So to spell out more clearly the circle invariance, let me say this again. So L is Hamiltonian isotopic through circle invariant Hamiltonian isotopies to a circle invariant special Lagrangian if and only if L cannot be destabilized by a circle invariant configuration. Okay, so if you cannot. Yeah,
excuse me, can I ask a question? Yeah, could you please go back to your previous slide?
Yeah.
So this condition of being unstable, so suppose L is stable and it's Hamiltonian isotopic to some L1 connect some L2, then you are saying that this averaging should be strictly less than the other.
Yes, right? the first one should be strictly less than that of the second.
But would that mean that it's unstable with respect to L2 connect some L1?
No, but you see, is that L2 connects some L1 need not be in the same Hamiltonian isotopic class as L1 connects some L2. So
Oh, I
they are
see. I
not the
see.
same thing.
Okay,
Okay.
okay. But it can happen that a Lagrangian might be unstable with respect to some Hamiltonian isotopic class, but could be stable with respect to another, right?
No, but a Lagrangian, when you start with a Lagrangian, the Hamiltonian isotopic class is fixed.
Okay,
So
I see.
let me say one more thing that may clarify your question. So
Mhm.
there may be different ways to break. If you start with a Lagrangian,
Mhm.
so the Hamiltonian isotopic class is fixed, but you may
Okay.
be able to break it into Lagrangian connect sums in different ways. Okay.
Okay.
And then it may be that in one way you cannot find that it was unstable. I mean,
Okay.
you broke it in one way and you found that the average grading of the first is strictly less than that of the second.
Mhm.
So you still don't know if it is stable or unstable.
Mhm.
But then there is another way to break it where you can see that it is actually unstable. You see?
Okay. Okay.
So to test stability, you need to check all the possible ways of breaking it up.
Oh, I
Okay?
see. Okay. 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 Thanks.
Yeah, you're welcome. Okay, so this was our first theorem. And now, as the notion of stability for the Thomas-Yau conjecture is different, we refer to it as flow stability. And also remember that there was this work of André Neves that said that you need to add at least one hypothesis, one extra hypothesis to the Thomas-Yau conjecture. And under that extra hypothesis, which is being almost calibrated means that the total variation of the grading is strictly less than pi. Okay, so that's basically it. If you look at the Lagrangian angle, which is a function that takes values in the circle in C, then it lies in a half space. That's what it means. Okay. And under that extra assumption, Jason and myself can prove the following, which is also a version of the Thomas-Yau conjecture. So if you start with a circle invariant Lagrangian sphere, which is now flow stable and almost calibrated, then the Lagrangian mean curvature of flow starting at it exists for all time and smoothly converges to the unique circle invariant Lagrangian in its Hamiltonian isotopic class, given by whose existence you know by the first theorem. Okay, so if there are no questions, I will now explain vaguely how we prove these things.
Gonçalo,
Yeah.
is the uniqueness also only for this special kind of Hamiltonian isotopies that preserves the circle action?
Yes.
So a priori, I could have another special Lagrangian, but I wouldn't get to that within with a Hamiltonian isotopy that would preserve the circle action.
Yeah, I don't think they exist.
Yeah, I mean neither, but
but so far I have no way to say that they don't.
Okay.
But the circle invariant ones are unique.
Okay, I have a question as well.
Yes.
So in the beginning, again, you said that by the mirror correspondence, then at the other side of this, there's a connection on a holomorphic bundle sitting somewhere, right? So what is happening? What does this Lagrangian stability condition imply when you look at the bundle picture? What
no,
is
in
the
the bundle picture, this is slope stability. It's the Donaldson-Uhlenbeck-Yau theorem. What motivates this in the mirror side?
Okay, and what about flow stable and almost calibrated?
Oh, so flow stable is it doesn't quite have an analog. It's flow stable is stable plus something else, and almost calibrated. I also don't think it has an analog because you see, if you start with any if you have a stable bundle and you start with any Hermitian metric on it, then the flow will converge for all time, will exist for all time, and converge at infinity to the Hermitian-Mills connection. So you don't need to add this extra hypothesis. So mirror symmetry, at least in the way I've been using it to motivate, it serves only as a motivation, but there aren't exact analogs of all the things. So geometrically, this side is more complicated.
I see. So it's not really a sort of involution of sorts. You can't move back from the gauge theory perspective to the submanifolds perspective without specifying extra information.
Yeah. So mirror symmetry, homological mirror symmetry, is a precise statement regarding the equivalence of two categories. Now, in one of these categories, which is the one talking about Lagrangians, which is the Fukaya category, some of the geometric meaning of some things is not clear. Okay, so you can't translate things. You can translate things algebraically, but geometrically, it's not clear what they mean. So I don't know. I don't think this flow stability, as I'm not sure there is an exact analog of it for bundles, and almost calibrated also not. And in the bundle case, everything regarding the flow seems to be much easier.
Okay.
Okay, that's all I can say. I don't know.
I mean,
other questions?
I can ask more. I can ask more during the question session. Yeah, of course.
Okay.
So I have a more naive question. When you say flow stability, do you mean like it's stable with respect to the second variation of the volume functional?
No. I'm sorry. No, it does not mean that. Because look, you are not even at the critical point of the volume function. You don't need to start with the critical point of the volume function.
Oh, so do you mean like if you start close enough, then the flow converges to?
No. This is another notion. I will say in the example what this means.
Okay.
It's not. You don't need to start close to it. You can start very far away.
Oh, I see.
Yeah.
Okay. Thanks.
Okay, so let's go and prove the first theorem. This first one. Okay, so the four manifolds we have, they come with a projection to R3. Okay, and this projection is basically the moment map, the hyperkähler moment map for the circle action. So mu1, mu2, and mu3 are the moment maps for omega1, omega2, and omega3. And these, you put them together in a map to R3, and away from a discrete set of points, this is a circle bundle, while above each of these points, you only have a point, really. And the circle invariant surface in one of these manifolds must be the preimage of a curve in R3. Okay, so let's do, I'll show you some more pictures. So let's go to this picture here. Okay, so this picture has here our manifold X. Then you have this projection mu down to R3. And then on red, in red, you have these points from S. And I've drawn here some curves, gamma 1 and gamma 2, and their preimages, which are some circle invariant surfaces. So if you pick a simple closed curve in R3, and you look at its preimage, and it doesn't intersect any point of S, then you get a torus, because above any point of the curve, you have a circle, and this becomes a torus, you see? Well, if I start in a point of S, and I end in a point of S, like in this curve, gamma 2, then above each of these endpoints, I only have a point while above any interior point of the curve, I have a circle. So these circles collapse to a point in both ends, and I get a sphere, a two-sphere. Okay, so these are examples of these circle invariant surfaces. And now I'll go back to the top. Okay, so these are the examples. This was basically the first example that I showed you. So if you pick a simple closed curve which does not intersect the points of S, then its pre-image is a two torus. And if you pick a curve whose endpoints are in S, then and does not intersect S anywhere else, then you get a two-sphere above. And now, when is such a circle invariant surface Lagrangian? And the answer is that it is Lagrangian with respect to some of these symplectic structures, if and only if it lies in a plane. So it must be planar, this curve, for it to be Lagrangian. And without loss of generality, so let's say we pick the first symplectic structure, the omega-1, then it needs to be perpendicular to the mu1 axis. Okay, so it needs to lie in a plane perpendicular to the mu1 axis.
So these mu-i's are moment maps for the same circle action with respect to the different symplectic forms?
Exactly. Yeah. Okay, and now when are these two Lagrangians like this, which are circle invariant, Hamiltonian isotopic? And the answer is they are Hamiltonian isotopic if and only if the two curves themselves can be isotope to one another through plane curves, so they must remain planar, and not intersecting and without passing through points of S, without passing through those singular points. So let me show you a picture of that. So here you have a picture of a plane in R3, and you have some points, some of these singular points, some of these points of S, above which you only have a point, and above all the other points you have circles. And now, for example, the curves gamma1 and gamma2 here, they are Hamiltonian, they are isotopic, but these curves gamma 1 and gamma 2 are not isotopic to gamma tilde, because in order to isotope gamma tilde, you must pass through this point of S and through this point of S. And
do you assume that all the singular points are in that same plane?
You don't need to, but if you do, then these things are actually, yeah, that's an important question. I don't need to for this work, but for the work that now Jason and myself are doing, we do assume that sometimes, because in those cases, these manifolds are Liouville, and then the Fukaya category is more well understood, and we can rely on some things that Paul Seidel does. But for today, we don't need to assume that all the points lie in a plane. Okay. Yeah. Thank you for the question.
The singularities are always points, or you could have?
They are always points.
Even in R3.
Yeah.
Okay.
Okay. So. Okay.
Also, just double check. Are you sure about the if and only if? Do you have a proof that they are not Hamiltonian isotopic, or just that you can't see it in Hamiltonian isotopic?
Yeah. That follows from Seidel's work also. Because you can
But this is only for spheres. You're saying?
Yes. Well, when we can state things more generally, but then it ends up only being for spheres, because you need to work with Maslow's zero Lagrangians, and then they need to be spheres.
Okay.
Yeah, but it is true what is stated here, that it is an if and only if. But that requires using some results from Paul Seidel on generalized M twists. Okay, so, and on their Hamiltonian isotopic classes. Yeah. So, and then the grading, what is the grading? How can you read the grading from these pictures that I've drawn? Then the grading actually coincides with the angle that the velocity vector of the curve makes with the fixed line in the plane where it is, okay? So you may be up to shifting all the gradings by the same constant, you may just fix one line there and declare the gradings to be the angle that the curves make with that line, okay? The angle that their velocity vector makes with that line. Okay, so now I need to show you what stability means. Okay, so that's this picture. So let me try to make this a bit smaller. So let's do here a Lagrangian connect sum. Let's say I have this gamma 1, which goes from this point to that point, and I have gamma 2. So this corresponds to Lagrangian spheres, and I'm going to form gamma 1 connect sum gamma 2. So what you need to do is to follow gamma 1, and then you go round the intersection point in a clockwise manner, and then you follow gamma 2 up to until the end. Okay? And this is gamma 1 connect sum gamma 2. And if you check here the angles, you see that let's fix L to be the straight line connecting the endpoints of gamma 1 connect sum gamma 2. So it's this line here in blue. Then you see that the first angle here, which is the angle that gamma 1 makes, is bigger than the angle that gamma 2 makes with it, which is this one. This one is smaller than 0, while this one is greater than 0. So this is unstable, okay? And now let's see a stable one. So now let's say that you start with gamma 2, and then you connect some with gamma 1. So you go around the intersection point in a clockwise manner, you see? So clockwise manner departing from gamma 2 to gamma 1. Wait. And then you follow gamma 1 until the end. Sorry?
This is anti-clockwise.
No, this is clockwise because it goes like this. Clockwise round the intersection point. The intersection point is above.
Oh, I see. I see.
Yeah, so, and now you can see that the angle of the first one is actually smaller than the angle of the last one. And so this is stable. And now you can see, well, in the unstable case, I cannot isotope gamma 1 connect sum gamma 2 to the straight line because I would have to pass through that point here in the middle, which doesn't allow me to cross it. But in the stable case, I can isotope gamma 2 connect sum gamma 2 to the straight line. And the straight line is the thing that represents the special Lagrangian because it minimizes area, okay, right? So that is actually true, okay? So the straight line represents the special Lagrangian representative of this Hamiltonian isotopic class, of this homology class, I'm sorry. Okay, so, and so you can see here, this is Hamiltonian isotopic to the special Lagrangian, and in this case, it is not Hamiltonian isotopic to the special Lagrangian, which is the straight line. Okay, oh, sorry, I didn't want to do this. I want to come here. Okay, so that is basically the proof. So, I mean, the proof is more complicated, but once you have this picture in mind, you can actually sit down and carry out the proof. So the Lagrangian is stable if and only if the curve is isotopic to the straight line connecting its endpoints, and this straight line represents the unique circle invariant special Lagrangian in the homology class of the initial Lagrangian. Is there any question here?
I think it's cool.
Okay, so good. So let's go to the Thomas-Yau conjecture now. So I'll go a bit faster on this. So we start with a circle invariant Lagrangian, which we now assume to be almost calibrated and flow stable. So almost calibrated, remember, means that the variation of the Lagrangian angle is strictly less than pi. So that means that the angle that the velocity vector of the curve makes can't vary more than in a half space, in a half plane. Okay, so you can't wind around and so on. And flow stable, basically, I will tell you in a second what it means once you dig it down. So the key observation is that the mean curvature flow of LT starting at L0 descends to a modified version of the curve shortening flow for the curve. And this flow is such that the curve remains in the plane, which is equivalent to this guy remaining continue to be Lagrangian. The area decreases, the area of the Lagrangian decreases because it follows the Lagrangian mean curvature flow, and so does the length of the curve. These actually differ by a constant, 2 pi, which is the length of the circles. And then flow stability of the initial Lagrangian says that for any way to break the initial curve you start with as a connect sum, then the length of the breaking is bigger than the length of the initial curve you start with, okay? So this is what flow stable means. Flow stable means that if you break it as a connect sum, then you have increased the length. But given that the flow decreases the length, this cannot happen along the flow. You can't see it breaking along the flow, which says that the curve along the flow cannot cross one of those singularities, one of those points of S. So that is very important. So it must stay away from those points. And then the other important point is that the grading satisfies the heat equation. And if it satisfies the heat equation, then that means that the points of maximum heat heat up the points around it. So the maximums of temperature shrink and the minimums of temperature increase. And so it must continue to be almost calibrated. So the total variation must shrink because it satisfies the heat equation. So it continues almost calibrated. And then it follows from a recent work on the blow-up analysis, on a recent work classifying Gaussian solutions to the Lagrangian mean curvature flow. So that follows from the work of Ben Lambert, Jason Lotay, and Felix Schulz. So Jason was my collaborator in this, as I said several times already. So this shows that no singularities occur from a blow-up analysis and comparing to this classification. Basically, the important thing in staying almost calibrated is that you rule out 2 planes forming, okay? Because if you go around one plane and come back, so 2 lines forming in this case, and then you come back around the same line, then you would have a total variation which is pi, which can't happen. And then the flow must converge to the straight line connecting its endpoints. And let me put it in this way so that thing doesn't disturb. And so you must be converging to the special Lagrangian as t goes to plus infinity. So this proves the 2 main theorems. And now I want to say one more thing about, just to touch a little bit more on stability regarding Jordan-Holder infiltrations for Lagrangians. So basically the role of the next thing I want to say is that I want to somehow motivate the following slogan, that special Lagrangians are the building blocks to make more complicated Lagrangians somehow. But before I start, is there any question?
I have a question, sorry. I don't remember so well, but if I seem to remember that the second statement had an additional something about the flow converging. But the proof you gave of the first statement, does it also not suggest that the flow should also converge?
Yeah, that picture I showed does suggest.
The first theorem I meant, sorry.
Yeah, so the picture I make in the first theorem suggests that this strategy will work. But you see, it could happen that, let me see if I can show you here the picture. So the difference between stability and flow stability is that, for example, imagine in this picture I made here. So this guy here is stable, okay? But if I imagine I go like this, I go out of this point and then I go very far here and then I come back to there, that thing is still stable, but it's not flow stable, okay? Because that thing would have bigger length than breaking it up like this, okay? So flow stability is a stronger condition that says that I'm not just stable, I actually chose a quite neat Lagrangian. Regarding the extra condition, so the extra condition is this almost calibrated thing. That is important in order to do this blow-up analysis and rule out the formation of those double planes.
Okay, thank you.
Yeah, actually, I can also make a picture at the end of Andre Neves' example of what goes wrong if you don't assume almost calibrated. If there is interest in that, I can make a picture and show it to you in the end. That is quite nice, actually. So, but anyway. So
again, you're assuming that L is always compact. The Lagrangian itself is compact.
Yes, yes.
And also, you don't see in your way of seeing the Lagrangians, you're never gonna see a special Lagrangian that's not a sphere, because they need to have constant angles, so they need to be in a constant line, right?
Yeah. All special Lagrangians that I see are spheres. Yes.
Okay.
Okay, so, but you can have like pinch spheres. Imagine you have 3 points in a line, and then you trace a line from the first one to the last one. Then you have 2 spheres intersecting at a point, or a pinched sphere. You see what I'm saying? So you have immersed Lagrangians like that, immersed special Lagrangians like that.
Yeah.
But it's not an additional assumption, right? You don't need to assume that there's nothing with genus that satisfies these.
No. Actually, so let me go show you the statement. I wrote here in the statement that I start with a sphere, but I don't need to do that. I can replace this by the following. Let L be a circle invariant, compact, zero Maslov Lagrangian. Then the thing follows. Okay?
And in particular, it's a sphere.
Yeah, zero Maslov and circle invariant will imply it is a sphere. And compact, sorry. Okay, so let's say what, let's go on with this. So I will say that one Lagrangian is a subobject of another Lagrangian, and I'll write it in this way to remind you of the group theory notation. If the second Lagrangian, so the big one, the one that has L1 as a subobject, can be broken as a Lagrangian connect sum of the first with something else. And that something else, I write it as a quotient, okay? L backslash L1. And then another Jordan-Holden filtration of L is a sequence of Lagrangians that is maximal in the sense that the consecutive quotients are stable. So you should compare this as a composition series in group theory. So when you have a group and you find a maximal group such that the quotient is a simple group, that is what you should compare this with. So this is the analog of a composition theories in group theory. So you are trying to somehow understand a Lagrangian by simpler Lagrangians, which are the stable ones. And you break it down by the maximal subobjects, so that the thing here are stable. So that's maximal in that sense. And then you further require that the average grading of the Lagrangians satisfies this is monotonous in this manner. Okay, so this doesn't matter. Jordan-Holder decomposition is the singular union of all of those. Doesn't matter so much. I'm not going to say that. Then another theorem we can prove is the following. So let L be a graded Lagrangian sphere with beta, which is the grading, a perfect Morse function. Then it admits a graded Jordan-Holder filtration. And the proof, it's quite easy. So let's go on. I need to show you a picture here, but let's start without the picture. So if beta, the grading, is a perfect Morse function, then it can only, and your Lagrangian is a sphere, then it can only have two critical points. But if it is circle invariant, the critical points need to be at the endpoints of the curve, right? Because otherwise you would have a circle of critical points. So one of them is the minimum, the other one is the maximum. And a computation which you can do is that the derivative of the Lagrangian angle of the grading as a function on the curve is actually the curvature of the curve. And so if it doesn't vanish other than at the endpoints, then the curve must be convex, must be enclose a convex region, because it has either positive or negative curvature. Also, let me show you a picture. So it's not this one, it's this one. Okay, so you have, so here I did not quite draw a convex curve actually, but anyway, suppose I did. Then suppose it encloses a convex region. I should have been more carefully drawing this curve. Then you can look at the following. At this big triangle is the convex hull of the singularity, so the points of S in the interior of gamma union L. So L is a straight line, and you look at the convex hull of all the singularities, okay? Then if you do that, then you can see that the curve gamma, there is no singularity in between gamma and the union of the boundary of this convex hull, which is a union of straight lines connecting these points. So gamma is actually isotopic to the connect sum of all those lines. So you have here in 1, 2, 3, 4. Okay, so this shows that gamma is isotopic to this connect sum, right? And then you can do the following. You can define gamma 1 to be the first one, then gamma 2 to be the connect sum of the first one and the second, up to gamma k, which is the connect sum of all of them. And how do I take this crap out of here? Okay, so we have gamma k, which is the connect sum of all of them, and you define Li to be the preimage of these gamma i's. And then you can see that the consecutive quotients, so take for instance here, L4, which is basically gamma, which is this connect sum, quotiented out by the previous one, which is gamma 3, which is all the connect sums up to here. The quotient is just L4, which is a special Lagrangian, so it is stable. And you can further see that these angles, which are the average gradings, so that which are the average value of the tangent of the angle that the tangent vector makes, which you can compute to be basically the angle that is made by the straight line connecting its endpoints, is decreasing as you continue doing this. So, and this is basically the proof. So let me go back to the slide. Where is? So the proof goes as follows. So you have that the curve union with the straight line connecting its endpoints encloses a convex region. you draw the convex hull of all the singularities inside this convex region. Its boundary is a union of straight lines together with a straight line connecting its endpoints. Then gamma is Hamiltonian isotopic to the connect sum of all these straight lines that are on the outer boundary. This is because there were no singularities in between both of these. And now you define these curves and you take the Lagrangians given by their preimage. The consecutive quotients are stable by construction because they are special Lagrangians. These things are also decreasing by construction because these are the angles between the straight line connecting the endpoints of gamma and the straight line connecting the endpoints of the gamma i's. And this is what I already said. And so this is basically to motivate that you should maybe compare special Lagrangians to, in terms of these Jordan-Holden filtrations, to the role that the simple groups play in group theory. Or I don't know, I think the whole nomenclature comes from more abstract categorical constructions. But if you disregard maybe category theory and just think about groups, already serves as a motivation for more or less the. And this is what I wanted to say. That's all. Thank you.
Okay, thank you. Right, so thank you. We have time for a few questions. Let me just stress an announcement. Made in the beginning, if you're late, you can subscribe to the webinar by messaging us or by sending an email. And if you do send us an email, you also henceforth receive an invite on the Google agenda, so you can schedule attendance for all future talks. As the first question, I believe we have an explanation of a little bit of the correspondence, of the mirror correspondence we heard from in the beginning by Marcos Jardim. Marcos, are you there? Can you explain us a bit what's going on?
Yes, I am. Yeah, if you guys can are curious, I can tell you a little bit.
Sure.
So maybe I can share my screen as well with something here.
Go ahead. It's in the bottom right corner.
Mm-hmm. Hold on. I do this all the time, but now I'm messing it up.
Well, while Marcos is setting it up, do you have any other questions?
I have a question.
Go ahead.
Yeah.
Do you, maybe, I don't remember if I've asked you this before, but these nice kind of Lefschetz vibration type pictures for in symplectic geometry are very useful when studying mirror symmetry to get generators for Fukaya categories that you then match with things on the B side. Have you tried to?
Can you say again the question, Luis? I'm sorry.
Sorry, I don't know. Maybe my connection is not so good. I'm just saying, on the symplectic side, people often use these Lefschetz vibration style pictures to come up with candidates for generators for Fukaya categories and to actually prove that they generate by computing Lagrangian Floer homologies. Like these Lefschetz vibration models are very useful for that. And then maybe, like, if you're lucky, you can study the complex geometry of the candidate mirror and find generators and match, prove that the Floer homology groups on one side correspond to are isomorphic to the X groups on the other side, and that's one way of proving homological mirror symmetry. I was just wondering, and people have recently been thinking about homological mirror symmetry for examples of K3 surfaces. There's very interesting work happening now. So I was just wondering if you have thought about any of that, try to use these models to do calculations in Fukaya categories.
Yeah, so in for Lefschetz vibrations, I think you do understand the Fukaya category well, and some of our examples when all the singularities are on a plane and they are Lefschetz vibrations. And I think Paul Seidel's book, this book here, does explain the Fukaya category does construct the Fukaya category in these cases. I don't know if it has I think it does have a finite set of generators that is understood well, which are the Lefschetz symbols. Regarding more general about, but we do have examples that are more complicated when the points the singular points do not lie all in a plane. And in those cases, I don't know how far off these things are. You can imagine that you pick different planes and you can try to put things together, but I don't know how different it will be, because if they are not in the same plane, then there are some extra holomorphic disks that you can see by hand. But anyway, so maybe we're going back to the case 3 case. I did think a little bit about whether there are some interesting circle invariant symplectic structures on case 3 surfaces for which you can do these things, and there are. But I think it would be relatively straightforward to do these things that Jason and I did for those symplectic structures on case 3 surfaces. We have a remark about that in our paper. But regarding the more sophisticated things on Bridgeland stability we are doing now, I do not know whether it would be feasible to do them for those case 3 surfaces with those symplectic structures. But yeah, okay. I do think that some things, for some symplectic structures on case 3 surfaces, you can do exactly the same thing we did, just with a bit extra work maybe to keep control of error terms.
Okay, great.
Sorry, let me just finish this thing. There are even Ricci flat killer metrics on case 3 surfaces that obviously are not circle invariant, but they are very close to being circle invariant. There is a work of Lorenzo Foscolo that constructs such, and for those, I think it would be also an interesting challenge to try to do this, because in that case, the notion of special Lagrangian does make sense in any way. In the more, I mean, you may want to think of special Lagrangians only when you have a Ricci flat killer metric, and in that case, you can think of them. You may also want to define special Lagrangians even if you don't have one, and you could try to do something exactly like we did, and that works. But if you insist that you have the Ricci flat killer metric, then you need to work a bit more. But I think you can do it.
Okay, thanks, Marcus. Are you ready for the next question?
Let me just see. Renato wanted to ask me something.
Okay.
I just want to ask if you take just M2, M3, and forget about M1, would that be a Lefschetz vibration, at least with symplectic fibers?
What is M1? What is M1?
M1 is the moment map with respect to omega 1.
Yeah, I see. Yes. Mu1, Mu2, or Mu2, Mu3 in this case is a left. It's a Lefschetz vibration.
Okay. And in this case, I mean, all the singularities would kind of like project to this plane in a way.
You need to assume that all the singularities are in a plane, and then Mu2, Mu3 is a Lefschetz vibration.
If the other singularity is not in a plane, it's just going to happen in another height. But if you just consider mu2 and mu3, it's still going to be singular for that point lying under the projection, right?
But I mean, you do have an holomorphic map always to see, but it could be that the Lefschetz symbols will not be just spheres. It will be disconnected spheres, unions of disconnected spheres.
Okay. Marcus, Jadim, now are you ready?
Yes, I am.
Go ahead.
My microphone is on.
Yeah.
Yeah.
Are you going to share your screen?
Yes. Is it showing now? I made a.
It is now. It is now.
Yeah. So the baby model of this mirror symmetry goes as follows. So you start on one hand with a two-dimensional torus. This thing here is supposed to be a 2.
Okay.
Right?
Okay, it's a 2.
So you have a two-dimensional torus on one side, and you have the dual two-dimensional torus on the other side. By the dual torus, I mean if this torus here is a product of two circles of radius A and B, say, this would be a torus, a product of circles of radii 1 over A and 1 over B, essentially. And then there is, various names, but Fourier-Mukai transform does the following. On one hand, you start with a holomorphic bundle on this side of the torus, and you end up with a collection of points on the other side of the torus. That's, more or less what the Fourier-Mukai transform does. Now, these Calabi-Yau fourfold Calabi-Yau surfaces, or hyperkähler manifolds that Gonçalo was speaking about, they have projections onto P1, onto CP1, right? So this is a CP1. And the fibers are toroid. At least generically, the fibers are toroid. So if you have a holomorphic bundle on this side, oops. So if you have a holomorphic bundle E on this side, and you do a version of this Fourier-Mukai transform, what you end up with is a bunch of points on the other side, right? So this is going to be some covering, branched covering of the base here of P1. And this curve that you end up here by varying the points as you move along the various fibers of this vibration, this wiggled red line that I drew here is a special Lagrangian. Not only is a sort of a multi-section of this vibration, but it's a special Lagrangian. And you can explicitly write down, if you have not only a holomorphic connection, but you have a specific anti-self-dual connection on this side, you can write a line bundle, or generally it's a line bundle with a connection, some transformed connection supported on this special Lagrangian base. Yeah, so that's the baby version, how you go from holomorphic bundles and holomorphic bundles with appropriate connections on a hyperkähler manifold X to a line bundle with an appropriate connection on a special Lagrangian or a complex Lagrangian on the dual hyperkähler manifold X bar. And so that's more or less the story in 2 minutes.
Okay, thank you. Then, so Gonçalo, so this is then my question, because so if you start with a stable Lagrangian, right, and then what we hear is that on this sort of submanifold side, we need to make extra assumptions like almost calibrated and so on, and flow stable and so on. But if you start just with the stable Lagrangian and you look at it on the other side of the mirror, then you do get a stable holomorphic bundle with an initial connection. Now for that, you do have the usual Yang-Mills flow, which will converge to something. And if you look backwards, so why do the mean curvature flow at all? Why not just flow on the other side, which always converges?
Yeah, but the thing is that there is no this mirror symmetry story in this setting and in general. You don't know these maps. You don't know what things correspond to.
Aha. The point is that the limit exists, but you can't translate it back. Is that it?
I mean, we do know that if you start with a compatible connection on a stable holomorphic vector bundle, then the flow exists for all time and converges to an Hermitian Yang-Mills connection. If it is polystable, it is more difficult, and if it is unstable, we also, you don't understand the convergence at infinity. You know it doesn't converge, and there is some blow-up locus, but that is still under. So there are still things to be understood, also in the holomorphic, in the mirror side, but those things are already in the more complicated case when you start with an unstable thing. So when you start with a stable thing, then everything is fine. But you don't know if those things correspond to something on the initial side you start with, because I mean mirror symmetry is not proven. It's not it's a conjecture. Many of these things are maybe close to being science fiction.
Okay.
You really want to do things, understand things in this side, and you use, I think at least it was Richard Thomas' point of view at the time, to use the mirror symmetry only as a motivation to what you should do in this case.
It's okay. It's okay. It's a quarantine. It's a great time to watch science fiction anyway. Okay. If there are no further questions, maybe we can think. Yeah, go ahead. Yeah.
Gonçalo, so I think it was part of your original plan to talk about Bridgeland stability in the Fukaya category and so on. So this notion of stability for the special Lagrangians, is it a Bridgeland stability condition or something like this on the Fukaya category?
So I can show you the conjectures that on Bridgeland stability. Let me share this again and show. Let me pick up.
If this is too long a story, I can wait for your next talk on the subject. Okay.
Yeah, no, but there are. So let me just say it in words then. So there are some conjectures that there exists a Bridgeland stability condition on the Fukaya category or on some version of the Fukaya category where the central charge is integrating the holomorphic volume form on the Lagrangian. Okay.
Okay.
And in the definition of Bridgeland stability conditions, you have these. You define these stables with slope phi, say, right? We have these subcategories of stable objects of slope phi. Those things are supposed to be the special Lagrangians of phase of Lagrangian angle e to the I phi, or to the e to the I pi phi, something like that. Okay, so that is, and the conjecture is that there exists on the Fukaya category or on some version of it a Bridgeland stability condition with this central charge and these subcategories of stable objects or semi-stable objects. And there are some further conjectures on whether you can represent always a semi-stable object by an immersed, maybe immersed Lagrangian, special Lagrangian, sorry, or a smooth Lagrangian that is not, maybe not special Lagrangian, but almost, And those things in this setting, Jason and I can prove. And also we can prove some conjectures on the Lagrangian mean curvature flows starting with unstable Lagrangians, that in finite time you will have to do surgeries, and in infinite time you converge to some sort of broken union of special Lagrangians, which are some sort of union of stable objects. Okay. It's more or less the idea of the same idea of what happens in the mirror side in that setting, actually, that if you have an unstable bundle, that you can somehow look at its associated graded stable pieces. Mm-hmm. There is some analog of that.
Yeah, the Arden-Arazimov filtration, right?
Yeah, so this Jordan-Nolan filtration is supposed to be kind of like the mirror to the Arden-Arazimov filtration.
Okay.
But except that in this case, it seems, if what I'm going to say is wrong, it's my fault. But it seems to us that it's more complicated in the Lagrangian story. For example, if I start with a curve that looks like this, I don't think you can make the Arden-Arazimov, the analog of the Arden-Arazimov filtration very well for this curve. So you have singularities here or where it's red.
Okay.
Yeah, so the problem is that it goes up and down, you see, so that there are problems with the monotonicity. Mm-hmm. So we think that maybe it doesn't, the monotonicity may not work.
Okay. Good, Gonçalo, thank you.
Yeah.
All right. Any further questions? Well, if not, let's thank Gonçalo again.
Well, thank you.
And we'll see each other. We'll see each other again next week with Adrián Andrada from Córdoba.
Okay.
Have a great weekend, everyone. Thank you.
Yeah, thank you.